Yeah, I'm Kris. Hi, everyone. Kris Foster. I guess I'll start now. I'll share my screen, if that's all right. I'll tell you a little bit about myself. So I work for Oracle, who invented GraalVM, and I work with Wolfgang, and basically we do a bit of advocacy, a bit of working with customers who want to try out GraalVM, you know, proof of concepts, that kind of thing, answering questions, basically anything to do with GraalVM and also Java. So the flavor of this talk is basically about native image, which is one of the aspects of GraalVM that people are most interested in. GraalVM is other things as well. I did a talk to a London Java user group maybe a year ago, I think, on GraalVM, and I covered off, you know, all of the other areas then, but I'll give you a quick overview. So first off, it's a new JIT compiler for Java runtime. So we've got a new JIT compiler that offers basically, you know, efficiency, you know, faster speeds and more efficiency, and shows some really, you know, big performance improvements over Hotspot. And that alone is quite interesting, I think. The second thing that GraalVM is, I always like to talk about it being three things, you know, three pillars. The first one had been, you know, faster Java Scala. The second one being native image, which I'm going to talk about tonight, so I'll get back to that in a moment. And then the third thing, like I said, 3 is a magic number. The third thing is multilingual applications. You have the ability to run many different languages on the same platform, on the same language platform. So you can have JavaScript, Node.js, Python, all in Java, all interacting in the same runtime, in the same address space. And that's got, you know, a number of advantages. It's a new way of thinking about maybe building your applications where you can mix code from different languages seamlessly together. And for the hosted languages on GraalVM that sit on top of this, what we call the Truffle API that we've added to the Oracle Hotspot Java runtime, all of those languages can interop with zero overhead. So, you know, if you've got a JavaScript object, you can use it in Python, swap between them. But I'm not going to talk about that. Maybe I'll do another talk, plan another talk about that topic. So I'm going to talk about native image, what native image is, what you can do with it, and I'd like to try and take a practical approach. So we've got this workshop. It's going to be slightly kind of a different flavor to maybe what I'm used to, and we'll just have to, so bear with me. I hope this works. I sincerely hope this works. I'm going to post in the chat, if I can find the chat, a link to a GitHub repository that contains the code, and then also GitHub pages of the code, which basically is just a tutorial, right? And I'm going to work through that today. Feel free to interrupt me and asking questions, and I'll try and answer them as best I can. And hopefully everything will work, right? And at the end of it, you'll have a bit of a flavor of what you can do with GraalVM Native Image. So this is the workshop. It's split into a number of parts. We'll try and get through, you know, as many of these as we can in the time allowed. I'm going to firstly talk about what native image is. Won't take more than like 5-10 minutes. Then we're going to look at building a simple like native image application. So, I mean, that's like, you know, starting at ground zero. We'll be using a framework. All of these will be using Micronaut, but you don't have to use a framework. I'll talk a bit about the frameworks you can use, but again, there's not really tied to any framework. It's at the language runtime level. So, you know, frameworks can be layered on top and can make use of native image, but you're not tied to any of them. You have choices about what you want to do there. We're going to talk about assisted configuration, which is an important topic in GraalVM. I'll get to that, and how, you know, what tooling is available to make that easier, to make using GraalVM easier. We're going to talk about class initialization strategy. GraalVM is native image is a new way of thinking about initializing applications. So you have, like, when you compile your applications, I mean, that's your sort of classical build phase. But now there's another phase. There's the native image phase where we can build an application into a native image. But as part of that, we can pre-initialize your application. So we'll look at what the rules are around class initialization and what flexibility we have there. We're probably going to skip smaller deployment. Sure, go for it. Oh, okay, no worries. We're probably going to skip the smaller deployments, but basically that was just demoing a tool called UPX that allows you to create very small, fast extracting, self-extracting binary files from our native images. We're going to spend a little bit of time looking at deployment options because Docker obviously is going to be a very interesting deployment scenario for native image. And then if we have time, we'll talk about memory configuration, GC, and some of the enterprise features such as profile guided optimizations. So without further ado, excuse me, what is native image? Well, really you've probably seen it talked about as a way of taking a Java application and generating a single executable from it, a single binary file from it. So you might take your Java application that would normally need to be deployed with a Java runtime, and instead you can create a native image that's a single binary executable that you can run and has all of the functionality of your application. It has some advantages in that it will start faster than your app would on a Java runtime, and it would probably use significantly less memory as well. But another way to think about native image is that really it's a new way of thinking about building Java applications. So you've got your compile time phase, which is what typically happens, when you write your code and you compile it. But now we've got a new build time phase where some of the application can be initialized and some of it can even be run before you actually deploy it and run it. And then we have, what you would expect like a runtime phase. So it's a new way of thinking about building Java applications. And what that is really shifting the work. Some of the work that happens when you start up a JVM with your application on it, that's done repeatedly. Some of that could be shifted to a phase that's done once, and then that information snapshotted or saved somehow and then distributed, right? So that it doesn't need to be repeated. So there are, some very obvious benefits to running GraalVM Native Image, and this is why a lot of people, probably a lot of the publicity you've seen. In terms of memory consumption, it enables you to really reduce the memory consumption of your applications. So on the screen right now you can see like a bar chart, and what this really shows is a hello world application, and it's implemented in 3 frameworks, the same application, same functionality, implemented in Helidon from Oracle, Micronaut, and Quarkus from Red Hat. And the green bar shows the amount of memory that application will consume, kind of like on average resident set size, whilst it's running. And these are they're quite low actually for a Java application, but you can see that you're in the hundreds of megs range. Typically when you deploy like a Java app, I guess you wouldn't really deploy one with anything less than 512 meg of RAM maybe, if you didn't want to hit any issues with it falling over. Now the red bars on the same chart show the same application for each of the 3 frameworks, but now running as a native image. So it's doing the same job, it's running the same code, but now we're looking at tens of megs. So there's a significant reduction, and it's anything around maybe, so between 10 times and 5 times. So you could be looking at reducing your memory consumption by a 1/5. And when you're deploying to the cloud, obviously memory is one of the important things you pay for, right? So if you can reduce memory consumption without detrimentally affecting your performance, then you're saving money or you're scaling for free. And it also applies if you're running Java applications on premise, right? There's always a cost to expansion to support, the growing amount of apps an organization has. So if you can do more with your existing infrastructure, then you're scaling for free, you're reducing your capital expenditure. And we see a similar story. I'm going to show you another graph now. We see a similar story with startup times. I guess everyone can still hear me. I get paranoid every now and then that my mic's died and everyone's lost me. Shout if you can.
Yes, we can hear you.
Perfect, thank you. It's a very similar story when we look at startup time for native images. So again, we take our Java application It's the same hello world, fairly trivial app, and it's built. We've implemented the same thing on 3 frameworks: Helidon, Micronaut, Quarkus. And here we see startup times, in the seconds, basically. And that's no surprise, right? Starting an application in seconds to sometimes 10 seconds is not atypical. The same native image starts in tens of milliseconds, so that's a shift to almost being like instantaneous. And okay, that's cool, but what's the real benefit of that? I guess the real benefit of that comes in a number of different scenarios. So if you're looking at command line applications, perhaps not a big use case, but command line applications now start like a C-based application would, so straight away they're very responsive. But maybe more importantly, if you're looking at microservices or function as a service, startup time affects your latency, especially if you're in some sort of scaled environment. And that also affects your, SLAs. So if you're able to scale more dynamically, which you can do, maybe if your application can start, in tens of milliseconds versus seconds, you don't need to have as much infrastructure running, right? You don't need to have as many copies of your microservice running in order to deal with peaks. You can maybe, excuse me, you can maybe deal with just having fewer of them running and then scale up automatically. So there's even the possibility, I mean, I've seen some people talking about this, of scale to zero, right? You don't have anything running until you need to. And in the labs, Oracle Labs, there's been some work done around this, and it's quite interesting. Like nothing is running until a request for a service comes in, and then it starts up an image containing the microservice and then lets the microservice respond. So fast startup times, again, can save you money or just basically improve your application performance. A third benefit would be reduction in package size. So if you have very large, CI/CD kind of infrastructure, when you build a microservice or a function as a service, it might be, say for a microservice, it'll be packaged up as a Docker container. If it's Java based, you need to have a Java runtime in there. You need to have all the things the Java runtime needs. So your Docker container could easily be, 500 meg plus in size, which is fairly significant, right? Especially if you have to, pay for the storage of all these, or you're moving a lot of these around, or they're not cached and you're downloading them to start them. With native image, there is the possibility of really reducing the size of the Docker containers. So like a real world example I was involved in, containers, a logging service that was, 400, I think, 500, 450, I think it was, like meg in size, with the ability of native image to statically link libraries into itself. It means you don't actually have to have anything in there. First off, you don't have the JVM, because native image doesn't need the JVM once you've built a native image. The dependency on the JVM has gone. It's a self-contained executable. So you don't have the hundreds of megs, 350, I think, whatever the size is, of the JVM in your Docker container. So that's a big saving. But you can also strip everything else out. You can build a Docker container from scratch that has a statically linked executable in it. So there's no libraries, everything's linked, statically into the executable that you're running. So there's nothing in your Docker container apart from the app. So that can allow you to bring, package sizes like Docker's image sizes down from, hundreds of megs, gigs to under 100 meg, which is quite an achievement, I think. But the kind of side benefit of this is when you throw everything away, you've actually reduced your attack surface. The JVM's secure, obviously, but the more moving parts you have, a fast system, all of the things the JVM needs, it offers potential for more attack surface. By getting rid of everything, and only having your application, you have done quite a lot to ensure the security of your package container. So the four things that I like to think of as the benefits are, your memory reduction. You can really reduce memory consumption. Startup time will be much reduced on native image. So you take a Java app, turn it into a native image, it's almost going to start basically almost instantaneously compared to what it was starting before. your container sizes, how you package your application is going to reduce in size significantly. And there's also the possibility of improving the security by basically removing everything else apart from, you know, the bare bones of what you need, which is your application. But this, I wouldn't say this comes at a cost, but it's a different way of building applications, and there are things that you need to be aware of. It's a new way of building applications, and we'll touch on this. It has this idea of a closed world assumption. When we build a native image, the tooling, the native image tool, excuse me, needs to know everything that's going to go into the native image. So it crawls, you give it a starting point on your app, and it crawls the application and tries to find out what's referenced. So it statically initializes things and follows the references to things that are referenced in the thing that the class you statically initialized, and so on and so on. And it keeps doing this until it's reached a kind of a fixed point. But that means you can't do any dynamic functionality at runtime anymore. And you think that would be a problem, you know, but it turns out it's easy to work around for a lot of things. Not all things, obviously, but for a whole class of things. You know, the reflection can be figured out just by being aware of what the application does, right? Monitoring it and seeing what reflection happens, what things are loaded, you know, what class files are loaded dynamically, etc. And all of this information can be passed into the native image build. So at the build time, we capture the dynamic things that are happening at runtime, and we can pass them into the build time. So we can still preserve a lot of the dynamic nature of Java and statically compile it, basically. One of the things we do like to talk about, I mean, native image, you don't need to be bound to a particular framework. You don't even need to use a framework to use native image, but it is a new way of building things, and, you know, support for some libraries is more difficult. So if you use, if you use a framework typically has done a lot of the hard work, the heavy lifting, to make using native image easy for you. So if you say, for instance, use Micronaut, which we're going to use in this series of workshops, it will have captured a lot of special configuration information, or will build things in a certain way so that building a native image is easier out of it. It's kind of following the path of least resistance, right? You follow somebody else's design decisions, but these design decisions have been made with native image in mind, right? Micronaut is definitely, you know, focused on, one of the things it's focused on is being able to produce a native image. You know, Helidon, SC, the same. With Helidon SC, they're very focused on being able to produce a native image from any application. Spring Boot, there's a lot of work going on between the GraalVM team and the Pivotal Spring team in order to make Spring Boot applications trivial to run on top of native image. So choose a framework and your life will be easier, but there's absolutely no reason to not just try native image by itself. Has anyone got any questions at this point before we move on to the first workshop? We're all good? Please say if anything's unclear, or, you know, you've got any doubts. I mean, at the end of the day, just to recap, native image is all about taking a Java application, getting rid of the dependency on the JVM, and building a single binary file from it. And that has benefits, but it's also a new way of building applications. Too long didn't read, that's what it does.
Sorry, I came on late.
Oh, Steve Bolton.
Hi.
I used to work with you.
Yeah.
How you doing?
Good. Yeah, I've started using it a little bit, but it's good to get more knowledge. So I haven't been using it in production yet on the native image. So I've been using it converted to Quarkus. So
okay.
I've been using Quarkus, and so I've seen it through that.
Ah, well, no, definitely. Give me maybe after this is finished, you can hang on the call and say hello, and
Yeah.
it'd be nice to chat to you. So the first workshop is just really basic stuff, right? How do we build a native image? And, you know, at the top here, I've gone over the benefits again. You know, small standalone distribution, not requiring a JDK. good startup time profiles, you know, it wants to start fast, and a low memory footprint. So I'm going to switch over to a terminal, but I mean, the whole point of doing it this way is that you've got something to take home in terms of like a workshop that you can follow through, rather than just listening to me and everybody falling asleep or forgetting what I've said. So definitely please copy the links from the chat box if you're interested in following along. So I'm going to use Micronaut because I'm learning it, I like it. So I've got Micronaut installed already. We don't need to do this. I've installed GraalVM. Installing GraalVM, there are some notes on the homepage of this, how to do that, but it's easy, right? And it gets easier all the time. I'm using the Enterprise Edition, which is available under an OTN license, free for development, you know, evaluation, personal use. And I've installed the native image package. So when you install GraalVM, it comes with a package tool called GU, Graal Updater, that lets you install other, you know, optional packages. These might be languages such as JavaScript. Sorry, not JavaScript. That's installed as a default, such as Python, Ruby, FastR, things like that. The LLVM toolchain. So I've installed native image, and these are the bare minimum of what you need basically to carry along with this, to follow along with this workshop. You need Docker, you need Micronaut, you need GraalVM, and you need native image. So to save some time, I'm going to switch to my editor and a terminal session, and we're going to have a quick look at our test app that we're going to build. And it's nothing super complicated. So it's a command line app. We're starting out with a command line app. It's built in Micronauts. Micronaut's got some nice features for building command line apps. Uses a library called, or another project called Piccoli, so we can easily define command line options, which is nice. And we define a run method, and in that run method, we're going to use this class that I've defined elsewhere to compute some random prime numbers, right? And over here in my primes computer class, we've just got some fairly simplistic logic for calculating a prime number. The explanation of how it works is there if you're interested. But you haven't tuned in to find out the best way to find prime numbers. So I'm going to jump to showing you how to build this. So with okay, so I'm going to go into my workshop, and I'm going to go to the complete example. Now in the GitHub repository I've given you, inside, you know, it's left as an exercise for you to work through each of these workshops, you know. But if you're bored or you just want to get straight to the meat, inside every like workshop section, there's a complete folder that contains like a working solution. If you find any problems or if there are any defects, you know, do just clone the repository or create an issue and let me know. So this is our project. We build it with Gradle, and we can build a Java application. And then we can run our application. So we're only using like Graal at the moment as a Java runtime. Nothing very interesting here, but let's run our application just to make sure that everything is working. So I can never remember the parameters. Excuse me. Yeah, so here we go. So if I run this, it's going to give me some random primes below 100. Perfect. But we want to build a native image from this. So all you need to build a native image is the native image tool, right? Which is installed when you install GraalVM and then use the package manager to install the native image package. And it's a command line tool, right? That's now part of your Java distribution. Now, if I wanted to, I could, you know, type in native image, blah, 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 no server, and some various other things. And what I would do is I'd pass in a class path, you know, where to find the classes, the name of the application, the main class of the application that I want to be as my starting point, and then the name of, you know, how I want to package that application, what name I want to give the binary executable. But for ease, we're going to use Gradle, and it comes with, when you use Micronaut, it comes with very handy native image build option, which will put our native image into an application there. So if I steal my parameters, that's it. And then we run our native image.
Oh, we lost Kris.
Kris? He's just frozen.
Yeah, same thing.
It's reconnecting. It was too much to proceed for the native image, so prioritized the capacity and reduced it to Zoom. He's coming back.
Yeah, it does take a lot of memory, I think. Yeah, probably, yeah, you're right.
Yeah, trying to reconnect. I will message him on Slack.
Hi, can everyone hear me?
Yes.
I'm not sure what happened there.
You're missed very much.
Zoom kicked me out. I was panicking. So let me just shut down Slack. I don't think I need that as a distraction. Apologies for that. Really not sure what happened there. Yeah, so we were gonna just, so we timed the application, right? Running as a native image, and then we always get this wrong. Java versus Linux. I think it's L, maybe on Mac OS. Sorry, Mac versus Linux. Okay, so when I run it as a Java app, we can see how long it took, and more importantly, we can see, you know, the memory consumption there, right? Now, if we were to run that as a native image, user bin time, yeah. Let's compare that. So already we can see the number is, you know, the memory consumption is significantly smaller. This is like the residence set size, you know, and it's by an order of magnitude smaller. Yeah. So I'm not going to do the sum. It's too late, and I've drunk too much coffee today. But it's significantly smaller. And when we look at, like, you know, the amount of time used as well to run that app, okay, it's trivial, but the JVM does a lot when it starts up. So with native image, we're kind of getting rid of some of this stuff. We're moving some of the machinery that happens at runtime to this build phase. And I've got a slide that explains this quite well that I'll bring up now to try and talk you through what's going on with this. If you bear with me. So I guess you can still see my screen, right? So what happens when we're building a native image? So we've seen that we can take a Java application, right, and we get this single executable out of it, and great, it starts faster and uses less memory. And I waffled really about what's actually happening in this, but I think maybe a picture is probably going to be more useful. So when we build a native image, we're taking our application, we're taking our libraries, the JDK and the substrate VM, which is our stripped down native image VM. And all of those are going to be used by the native image tool. And the native image tool is going to be given a starting point. We're going to say, we'll start with this class. So it's going to find a method that it knows it can use as an entry point. And it's going to statically initialize this and crawl, any references that it can find within there that are initialized. And it repeats this until it reaches what's called a fixed point, a point where it can't find any changes. And as it's doing this, this static initialization, this finding out what's actually in the application, the first thing is it's doing a lot of dead code, very aggressive dead code elimination. So the size of your application is being shrunk. But also, which bits of the JVM do you use? And which bits don't you use? It's throwing away a lot of things, but it's also snapshotting the heap. So this static initialization gets saved into what we call the image heap that's kind of baked into the executable. So when the executable starts, loading that snapshot of the image heap directly into memory is a relatively fast operation. But then the heap for the app is now sort of pre-initialized. Some things will need to still be initialized. And we will look at that in one of the later workshops. But it's very much like this. We've got these different phases where like on the left-hand side, you've got like your basic Java application, right? We compile the code, then that's the build time done. Everything else happens in like a runtime context. We load our classes, we load our configuration, we run. What's happening when we build a native image is this middle column. You compile your classes, right? Well, that's like your classical development build time activity, I suppose you call it. But then the loading of the classes and some of the initialization of them is now being moved to build time. What gets initialized is the default is your application code is initialized at runtime, but large chunks of what we can determine to be safe code is now initialized at build time. Safe code of the JVM, sorry, is now initialized at build time. But we can push this idea even further, and GraalVM allows you to do that, where we can move some of our application code into the build time phase. So we could say that we want some of our application to be initialized when we make a native image. We can even run some of our code when we're building a native image. And this is more sort of advanced features, but it is totally possible to do. And by running some of your application in advance, there's work that happens almost maybe unnecessarily, repeatedly every time you start up your application on a JVM. The idea is, wouldn't it be great if we could push some of that back to a single event that happens rather than, constantly repeating this work? So hopefully we've seen, what a native image is, and that it's relatively easy to create one, and that the benefits are that we get great performance in terms of speed, startup speed, and memory consumption, basically. So does that make sense so far? We've shot through the first workshop. Please do shout. I really would appreciate it. Like, if you've got any questions, do stop me. It's not a problem.
Okay,
so, yeah. Hi.
Sorry, I actually have a question for what I've seen using the GraalVM compiler. Sorry, the agent that you can use to find out which classes are used by reflection. So I've noticed that if you don't explore all the paths in your code, of course, the agent won't see them, so it doesn't produce the configuration. So I'm wondering how practical is this when you have a complex application and if you need to find out by yourself which classes are used by reflection is not trivial, and the engine might miss them.
No, I mean, that's a fair point, right? The agent will only identify them if the code path gets executed, right? exercised. So there's, you know, a different way of thinking about this. You know, like what kind of application do you want to build a native image out of? You know, is it going to be maybe a super complicated one? Perhaps, you know, maybe you'd want to start with simpler things, you know, microservices. It's, you know, very well suited for that. There are probably fewer code paths. Also, if you exercise if you use the agent whilst you're, and I always sort of think this is a good idea, exercising all of your unique test cases as well as your integration tests, you're covering off a much bigger area of, you know, all possible paths. So that should identify most of the reflective kind of, or those kind of use cases. The other thing is as well, you know, this is probably more applicable to, like, you know, greenfield applications. If you're using a framework that's designed from the ground up, say like Micronaut, to target native image, you shouldn't really, I mean, they're going to be, like in the case of Micronaut, I wouldn't expect there to be any, but in maybe the case of Spring Boot, there may be some edge cases where some dynamic feature kind of leaks through. The good thing about, like, you know, about Micronaut, one of the good things I think about Micronaut is that it looks like something like Spring Boot. You know, you're using annotations all over the place, but the way annotations are used is different. They've moved to a build time phase with these annotation processes. So a lot of what looks like dynamic functionality can actually be pushed to like a compile time phase. There are always going to be some things that you just cannot replicate, right? I mean, if you're building a code editor, something that's really dynamic, right, like IntelliJ or, you know, Eclipse, or an application server, right? If you're building like a WebLogic server, say something that's continuously like loading classes, you know, doing stuff like that, native image might not be the best fit for now. I mean, who knows in the future, right? But that's my take on it. But I think that's a really valid point. Oh, no worries. Thank you for asking a question. I feel like I'm shouting into the void sometimes. So we're going to look at assisted configuration. Andrea has just mentioned that. So I talked about this closed world assumption. It's kind of an important idea. So I say so a lot, I've noticed, when I'm doing these talks. Must stop. The native image basically grew out of work to embed GraalVM into the database, the Oracle database. And a way to make, you know, the tight performance guarantees required, you know, for GraalVM to be in the database, like anything going into the database, you can imagine the extremely tight parameters about, you know, what that application can do. It had to be a very controlled environment, right? So that kind of gave the team working on native image like a new approach. You know, maybe we can do really aggressive dead code elimination by assuming we know everything that's going to happen in our application. So we can walk all of the possible paths and we can see what's used, what's not used, and we can use that information to really aggressively optimize the application. And that worked, right? It produced something that could be embedded in the database, but it also had like this side effect of producing Java apps that start fantastically fast and use not much memory compared to what the equivalent Java app would run. But obviously, there's a lot of Java applications that use reflection, you know, load resources from the class path, JNI, dynamic proxies, all of these kinds of things. And they wanted to see, you know, how far they could take native image and allow for these. And I guess the next obvious step was to say, well, you know, if you know that some reflection is happening, can we configure this? You know, can we tell the native image build tool that this is happening? Yes, we can. There's nothing to stop us doing that. So then, you know, native image knows about that and can allow for that, because that information is now being passed from a runtime context into like a build time context. But I mean, it's laborious to do, right, for anything beyond a simple application. So they built an agent, a Java agent, that you can plug into your Java application, and it will capture this information for you as you run your Java application. But as Andrea said, it's very important to make sure that you exercise all of the, you know, the possible class possible paths in your application. So good unit tests are important. So I'm going to move to a new example now. So if you give me 2 seconds, I'm going to close down my previous one. We're going to take a look at how we can use the Java agent. So let me open my Java class. So it's a really, silly application in a way, right? But what does it do? So if we start here, right, we've got a couple of classes in this app. The first one defines a string reverser. So you pass in a string and it reverses the string. So if I put in the word hello, I'll get ole out. And the next one is a capitalizer. Pass in a string, it'll capitalize it. And the main sort of framework for running this is this reflection example. And what this does is it'll take in some parameters. The first one of those is going to be a class name. So which of these 2 classes should I load? The second one will be the method name. So I'm loading string reverser. I'm going to want to use the reverse method. The final one will be the string that I'm going to operate on. Excuse me. And it's going to load the class dynamically, class for name. We're going to find the method on the class, and then we're going to try and invoke the method, passing in the input. So I guess we've all, seen examples like that. So let me go to the code. So I think I've compiled this already. Have I done that? Yeah, I have. Now I've got to rely on my memory, which is fairly poor. Okay, so we've run our little kind of test harness, and we could pass in a string reverser, and we reverse the strings, or string capitalizer. Okay, so this is an example of some, fairly dynamic Java programming. We're looking up classes and we're calling the methods on them to pace, totally based on what's happening at runtime. So if I was going to build a native image of this and try and run it, I've done that already. And let me show you building the native image, because it's a good example of how to build a native image. So let me steal my command line from here. There we go. I'll actually change that slightly. So I don't want a server. So I said earlier we could, you don't have to use a framework. Well, this is an example. I'm calling the native image, passing in some parameters. No server tells it not to start a build server. No fallback, to die a terrible death if if it can't build a native image, I just want it to die instead of trying to create a fallback executable which has dependency on a JVM. So let's run this. In this workshop, I'm going to try not to build native images too often, because this is another thing that you'll see about native image. It takes, they're not always very fast to build, and I guess that could be seen as like quite a negative thing, but I kind of think native image is an optimization step. You build your Java application, you make sure your Java application does what you want it to do, and then you move on to native image, building native images and solving any potential issues about turning your application into a native image. It's not supposed to be done as some kind of iterative development, because it will be quite painful for large applications. So that's run and created by XC. And pass in some parameters. Let's see what it does. It's working because I'm sloppy. That's why it's working. Let me rename this folder, because I've already, when I was testing this out earlier, I ran the agent to capture the dynamics information that would need to be passed to native image, and I forgot that it was still there, so I need to run it again. Apologies for that. Now what we should see when I run this, is that basically it throws an exception, because we're asking it to do some dynamic things. But when it built the native image, it optimized the hell out of it. It chucked a lot of things away. It's got no idea about any of these classes anymore because they were never explicitly referenced. It doesn't make for great television watching native image run, I have to admit. Okay, so now if I run my application, hooray! You don't often hear people cheer when they have an error, right? It says it can't find the class string reverser, and that is because if we look at my class here, there's no reference to string reverser or capitalizer in here. And this is the entry point for native image. So when native image does this iterative points to analysis, it finds no reference to either of these. So it assumes they're irrelevant. And as part of its very aggressive dead code analysis, it just gets rid of them. It says they're just not relevant to me. But that's not really any good if we want to do dynamic things like this. So what we can do instead is we can use this Java agent, and let's have a look at an example of this. So we're able to run our Java application. Let's copy it. And we're able to save the configuration information that contains all of the info about the classes, the dynamic stuff it's found, to the file system and feed it into the native image build. And we do this like using any Java agent. We can pass in the agent library, which is the native image one. This gets installed with the GraalVM runtime. And then we pass in some info, some configuration info. Where do we want the output directory to be? Where do we save these to? So whilst I'm running that, I've got to create the file. Sorry, I've got to create the directory. The application run, and now inside if this refreshes, we'll have a look at the old one. Right. Okay. We have some files in here. So if we take a look at some of these, let's take a look at reflect. So it's captured that I was using string reverser, but you see that there's no mention of a string capitalizer in there. I'd need to run the agent again using the capitalizer, passing in the capitalizer to the command path. And that's why it's important to run the Java agent against a set of unit tests, basically, and integration tests, so that you're exercising all of these examples. You'll have less of these kind of issues if you use a framework, though, because the framework has already done a lot of the work for capturing this kind of information. I won't do the native image build, but if I were to do the build, it would take these files, these JSON files, use them as configuration for the build process, and then the new native image would actually have information about those classes baked in. So if I use my reflection example, if I use my native image that I've got one I built earlier, hopefully, I think it's built with the reverser in place. We'll find out in a second. There we go. We'll take that. So now I'm calling the native image, and I'm just passing in the parameters before. Okay, didn't know about string reverser. I bet it was string capitalizer. Oh, I think it's probably because I can't actually spell. Actually, do you know what? Let's just rebuild the native image. And let's make sure that the config is there, the meta native image is there. Let's use that, and this time it should be aware of the reverser class, and when I call the native image, when I tell it to load the reverser class, it will be available in the native image. Let's just make sure before I make even more of an idiot of myself. Yeah, string reverser. Perfect. This is the danger of preparing things before. You never quite remember what you did. So anyway, we've shown that, hopefully you've seen that you can take dynamic features of Java, and using the native image agent, we're able to capture those and pass them through to a native image build step, and basically they're now able to be included in your native image build. So the fact that native image relies on this closed world assumption doesn't mean you can't use dynamic functionality. I mean, you shouldn't, if your code is heavily dynamic, I mean, you are going to hit problems probably, I guess, like if you're building a code editor, or like I said earlier, you know, some kind of application server, like you know, a servlet container or something. You may hit problems, right? But there are ways to work around a lot of the dynamic features of Java in native image. This doesn't mean you can't build native images from things that use dynamic code. So back to this, I mean, that's really what I wanted to show you with this, that, you know, even if you are using dynamic functionality of Java, you can still build native images from your code. Anyone got any questions? It's all right so far? Enjoying me making a fool of myself with my pre-prepared things. That is it good? Am I good to go on with the next section? Any questions? No? Okay, cool.
We had a question here for the testing capability, yeah, and we had some coverage in the code, yeah.
Oh, okay. Is this about, you know, as with the Java agent, you know, finding out what happens, you know, what dynamic stuff is happening?
Yeah, it was from Richard.
Yeah,
about,
I guess the question was around,
yeah,
you know, before those two methods, one of which you covered, and then the other one you said, oh yeah, I've actually not done that one. And it says, and you said that the approach is to have a, you know, a set of unit tests to make sure I've covered all my dynamic code. So you know, I can make sure at runtime nothing's going to fall over. Is there tooling in place that can almost tell me, yeah, you know, I've got all my dynamic code covered, I'm going to be okay running this statically almost?
That's a good question. I don't think there is a tool at the moment that will tell you, you know, whether all the dynamic paths are available. But I don't think that is almost, you know, I don't think that's an impossible thing to exist, right? In the same way that we're watching the Java code execute and seeing where dynamic code happens, I suppose you could do like some static analysis of the code and say, you know, here's an example of class 4 name, right? Just as one example, can we find those? I'm sure there must be static tooling that is around that does that.
I don't know. It sounds like you're asking for something that's Turing complete.
Well, no, good point, actually. Yes. Because, yeah, go on.
No, that's all I want to say. But I have a second question, which is, you mentioned that a lot of frameworks and Spring Boot was on your list. kind of have this sorted. How does that work? They've kind of done the analysis and include their own meta-inf, or I mean,
that's the kind of thing it's a mix of things. They've done so they've done a lot of the work in identifying, you know, the config. You know, some of the frameworks, say Micronaut, you know, don't rely on dynamic features like this. You know, they relies on annotation processing and pushing that to like an earlier stage. In terms of Spring Boot, they've done a lot of the configuration for you, but they've also written like features that plug into the native image build process that provides extra information about what's happening in the Spring app. Obviously, they know from, you know, a Spring point of view about all the kinds of things that are happening there, and they can provide extra information to help compile the application. So that's the work that's taking place in the Spring Boot native image feature. It's an experimental feature. Does that answer your question? I suppose maybe not.
Yes, thanks.
But I suppose what you were saying earlier, I mean, it's possible to load a class and then, you know, from a string, and that class could load other classes, and maybe you'd never know. Right, okay, let's move on. So just to recap on that last one, we've looked at building native images in the first step, and we've looked at how we can also like just keep track of how basically dynamic, if there are dynamic things happening in your native image, that doesn't mean you can't build a native image from your Java code, right? If you've got dynamic things happening in your Java code, you can still build a native image. And to do that, you want to use the Java agent, which will scan your code, but you need to have good coverage, or you need to have a lot of information about what's happening in your code. So we're going to take a look at class initialization strategy. And try and look at an example based around that. So earlier on, I talked about with native image, you know, some class initialization is happening now at this build phase. Excuse me, is happening at this build phase. And your application class initialization is happening at runtime, because that is the best default behavior for application correctness, basically. So what gets initialized where? I mean, there is good documentation on this, and I've referenced, you know, I tried to bring together some of the documentation around this to give you an idea of, you know, what happens where. But basically, you know, we've got this build time and a runtime. In the build time now, we try to like initialize things that we know for sure are safe and form part of either the substrate VM or the JDK. So these are important JDK classes: the garbage collector, and the deoptimizer. We also have, like, you know, other known safe classes that we feel comfortable initializing at build time. It's possible for you, even though your application classes are initialized at runtime, it is possible for them to be initialized at build time, but that's a kind of an opt-in feature. You have to make a decision, and we'll have a look at, in this example, how you could do that. So the example, we're going to take this kind of sort of fairly simple example, I say simple, basic example, where we've got a main class and two other classes, and, you know, the main class references class A and class A references class B. So there's this kind of chain of classes, and in the bottom of the chain of classes, we're going to use like one of the less standard char sets, like UTF-32, little endian, and we're going to try and print out the name of that char set. So when we run this as Java, we would expect it to print out UTF-32 LE. So let's compile this. Well, I think we've got it compiled already. I'm probably taking my life in my own hands here by okay. So it prints it out. And if we look at the code here, like I said, we have a main class. When that gets called, the main method, it's going to call static method B on A, okay, and B points to an instance of B that's stored in the static field. And when on B, we're then going to call the doIt method on the object, and that that doIt method is going to call this system out, which makes use of this UTF-32 char set. But if we build a native image of this, so to save time, I have built some here that should fail. We notice, so this is one I built earlier in true Blue Peter style, and I've called it fails, main 0 fails. This is where I've just built a native image from that class file. And if we look at the error message, we see that we have an unsupported char set exception, which might seem kind of cryptic. But what's happening here is that when we build a native image, one of the things we do is we don't include all of the Java char sets, because we want our native image to be small. We want them to be a kind of an opt-in. We can work around this by passing in a flag to native image to say include all char sets, and then our application, our native image would work fine. But that's maybe like a kind of a heavyweight way to solve the problem by bringing all of these char sets in. A better way, a possible better way, would be to maybe move the initialization of these classes A and B to the build time, because the native image build tool is just basically a Java process, right? So when it runs, if these are initialized at runtime, that char set will be available. Native image will know that that needs to be available for the application, and we'll make it available. It will package it into the native image that gets produced. And the way we would do this is by specifying some parameters when we do our native image build. So let's scroll forward. So this is when I was talking about, adding all the char sets. It's possible to use a parameter to add all the char sets into the native image, but we don't want to do that. What we can do instead is we could look at the class initialization and find out what gets initialized where. And if we were to do this, I think we can generate some reports, and we can see that like a runtime, our class A and our class B are initialized at runtime. But we can also, which is the kind of point I was getting to, we can initialize class A and class B at build time. We can tell the native image that we want both of those classes to be available at the time to be initialized, at the time of build, and therefore all of the things they need will be available. Native image will know that we'll have full visibility of everything, including the char set, and we'll package it in. So if we try this out, we're going to build our native image now, and this time A and B are going to be initialized build time. Which, if A and B were, like intensive in some way to build, or did something that was like an intensive operation, maybe feasibly, you'd want them to be initialized at build time to save the work, to do that work only once. But I mean, I guess it would depend on whatever, that work was that you were doing. So now I've built this application. It works by moving those classes to build at to be initialized at build time. Sorry, we solved our problem. But that you have to be careful about moving class initialization to build time for your own application classes, because there's a bunch of things that we can't have in our image heap. Like running threads, open files, network sockets, like random instances. All of these things make sense, not to bake into a native image, because some of them don't make sense to, and some of them could be really insecure, like baking in a random. So if we were to change our Java code and we would say to add a thread to class A, to its static initialization, so now there's a thread in there. When we build our application, our native image, we would then get an error message because it's going to say that you can't have a thread in you can't have a thread baked into a native image, and we can try that out, right? I think I've main1.java. I think this is, yeah, let's build this one, right? So if I've got another Java file there that contains the same stuff. Damn. I think I've compiled this. So let's see what this one says. It's probably going to complain and say that you can't have a thread baked into the native image. Yeah, okay, which is what it did. So you have to be careful, but the solution to that, I mean, we don't need to initialize a build time. We could maybe just initialize B at build time. I hope this works. And that would generate a native image for us. That should still work, right? Because B is what contains the reference to the char set that isn't by default baked into a native image. And we've also got the thread running, right, which was in A. So we've had a look at the possibilities of how you can move your application initialization into this native image build stage. It's not the default. The default is that only known safe classes in the JDK and certain important classes to native image are initialized at build time. Everything else is initialized at runtime. But if you want to, and you are careful about it, you are able to push some of the work that you're doing at runtime into this build phase. And that wraps up pretty much this kind of quick overview of class initialization. So I'm going to take a quick look at the time. I've probably got about 15 minutes left, so down to me waffling more than anything else. We've looked at so far, just a quick recap, building a simple native image, how the assisted configuration can help us with dynamic features of Java, so that dynamic features don't need to be a roadblock to making a native image. We've looked at class initialization, and maybe we'll take a quick look at deployment options and how you can build small Docker containers containing native images. So if you're building microservices, or maybe even function as service, you might well be packaging your chunks of application code into a Docker container. And as it stands at the moment, if you're using Java, there'll be a Java runtime in there, plus your code and libraries and a few other things that you will need to get the Java runtime running. It'd be good if you could get rid of some of these things. So the containers were smaller, the images were smaller, which is always nice, and also that they start faster. So a quick note, because you will bump into this. I mean, don't know if many of you are using Macs to work on. One feature of native image at the moment is that it doesn't support kind of cross compilation. So if I'm using native image on a Mac, what gets produced is a Mac executable. If I'm using native image on Linux, what gets produced is a Linux ELF file. Windows, a Windows binary. So if you're, if you want to achieve that kind of cross compilation, a pretty standard scenario is to use Docker to do your builds in. So if I'm using, I use a Mac So if I want to build a Linux Docker container, I have to do my build in Linux. I can't build my native image on my Mac natively and then copy it into a Docker container. And you'll see this cryptic error message. It's probably not that cryptic really, but whenever I forget about it, it always comes as a surprise. But if you see this, it means that you've basically got the wrong format executable for your Docker container. So if you're building, if you want to build a Linux native image, but you're on a platform other than Linux, then you need to do your build in Linux on a Docker image. So we're going to switch now to using we're going to take that basic app that we've been building with Micronaut, and now we're going to expose it as a microservice. And if we take a quick look at that, it's not dissimilar to the kind of thing you see in lots of other frameworks. There's some sort of annotation telling you the URL, and then some get parameters, get URL methods that show what parameters can be passed in, etc. And you can wrap up different bits of functionality in these. So we're going to build this, and we're going to get a Java application that's a microservice with a HTTP front end. Now, we can build that into a native image on my Mac, and that's all fine and dandy, but not that interesting. What we probably want to look at is, how we package that in a Docker container. Now, a typical scenario is to have like these two-step builds, where you have a Docker build file, that is really built of two parts. There's the first part, which is the build phase. This is where you get some kind of fat image and you use that to build your application. It's got all the things you need in, such as GraalVM Native Image, and any like development build essential stuff that might be needed in order to build native image. So all of the requirements that the native image tool might have. So you would use this to actually build your native image, and then you have a second step, which is the container that you're going to be deploying, your runtime container. And that takes the built artifact from the previous one and packages it up inside some kind of slim container. So if we look at this particular example, I've built this web app I've built a native image from it, and then I've packaged it in Oracle Linux, a slim Oracle Linux container. We're not going to build it because it takes some time, but we can have a look inside that container to see what sort of size it is. So there's a tool called Dive that lets you look around basically the layers in your Docker files. But I suppose the big thing here is the total image size, which is, let me highlight that better, 172 meg. So already, it's smaller than like the comparable Java Docker image would be for the same app, right? But that's still not as small as we would like to make it. So we can, and I hinted at this earlier, we can use really tiny Docker containers. And there's a couple of options in this kind of area. I mean, we could use from scratch containers, which have literally nothing in, or we can use distroless, which is a very, minimal, basically just the bare bones essentials. And those contain like a dynamic libc, but almost nothing else. So with native image, you're able to, when you build your native image, one of the things you can do is you can control whether libraries get statically linked into the binary that's produced. In this case, one of the flags, static executable with dynamic libc, allows us to link in everything apart from the libc, which will be loaded dynamically. And we can package that in a distroless container. And here's an example of that. I'm going to quickly show you this, and then we'll have a look at how big that container is compared to the previous one. So again, fat container is the builder. We build the application, and then from distroless, we're going to package in from our previous container, we're going to package previously. So previously it was 172 meg in size. Now it's going to be smaller. I think it's about 77 meg in size. So it's decreased a lot in size. We've managed to get rid of even more than we did just by making a native image and getting rid of the JVM. So it gives us an option to really, really shrink our containers. And again, like, you know, the less that is in them, I would argue probably maybe the more secure they are as well, right? There's less of an attack surface there, less moving parts. So this, you know, we can run this just to confirm that it really does work. And let's do this now. Okay, I think it's running on port 8080. Let me have a look. Yeah, so there we go. We're calling our app and we're getting some prime numbers back. Not particularly interesting, but it does show that, you know, with native image, you have a lot of flexibility in terms of like squishing things, right? Reducing what, you know, what goes into your like runtime environment. We've got rid of the, you know, it's possible to get rid of the JVM, but you can push it further with this static linking and get rid of even more. And the benefit of that obviously is, you know, smaller container sizes. So any questions? I covered that one at a bit of breakneck speed because we haven't got very long, I'm afraid, but anyone got any questions before we have a quick look at some of the remaining topics? I'm not sure how much we'll be able to do in the remaining time, but I'd like to at least talk about them. So,
sorry, I have a quick question, if that's okay.
Yep. Yeah, of course, please.
So when it comes to putting Java on Docker, you usually have to control some of the aspect of XMS and XMX to make sure that it can scale, right? So if you have 100,000 requests per second, you'd still be able to kind of cope with all of this. How can you do that with this setup, if I may ask?
Yeah, totally.
So this is that one.
Yeah. And so this is the next thing we're going to have a quick look at. You've got the same, you know, memory options in native image as you have with Java. You can control the heap, you control, you know, various different things. So here we've got an example of, you know, how you can configure the heap of the application when you're running it. You know, I can pass in -x 64 meg. But what you'll find is that, you know, your application will run significantly less memory. So the Spring Boot Pet Clinic app, I've got that working on native image where you know, I've constrained a Docker container to max 128 meg in size, and the application is operating, you know, happily when I stress test it with Hey, which is a stress testing app. Is happily operating at about 60 meg memory usage. I mean, if I try and run exactly the same code, but this time with Java on, you know, 256 meg of RAM, it falls over most of the time when I try and stress test it. So you've got the same control over the allocating the heap, you know, like how much memory you want to allocate as you have with Java. And you can also constrain the Docker containers, which is perhaps, if we're talking about constraining things, that's probably like a more meaningful thing to talk about. One of the things that like comes as a bit of a shock sometimes is that if you don't constrain the heap size, or you don't constrain the size of the container that you're running your native image in, it potentially can consume up to 80% of the available memory. So if I were to run my native image and it's got no constraints, and you know, I've got 16 gig of RAM available on my laptop, say, you know, you might see that it would be able, it might say that it's able to use up to 80% of that, right? It probably won't, but that's the kind of default for the JVM and also for native image in terms of allocating the heap. So you do have to be like aware that when you are running your application, if you give it lots of memory, it will look like it might want to try and use as much memory as it can get at some point. But that's not really a good example of like how little memory native image could use. if you want a kind of a like for like comparison, it makes more sense to, you know, either specify a heap size and constrain it that way, or, which I prefer, to, you know, constrain it inside a box, inside, say, a Docker container of a fixed amount of memory with no swap, ability to swap, and then try and run, you know, the Java application and the native image side by side to compare the memory consumption. It's just something to be aware of. But you have all of the same functionality for constraining the heap or increasing the heap as you do with the JVM. I don't know what the largest heap size you can have on native images. Actually, it's not as big. I mean, if you've got really big heaps, I think Java, you know, running GraalVM as a Java runtime is the right thing to do. If you're, you know, looking in, you know, massive heaps, then I don't think native image is the answer. If you've got kind of more normal sized heaps, you know, maybe tens, hundreds, gigabytes maybe of RAM, then native image should be fine. Does that answer your question?
Yes, it does. Thank you very much.
No worries. So, you know, that was one of the things I wanted to talk about anyway, which is the configuring memory usage. One of the other things is GC. So in native image, in the community edition, there's a relatively simple garbage collection implementation. And when you're using the community edition native image, there might be some kind of stop the world pauses for GC to take place, which you will see like manifesting itself in like the latency. So if you to plot a graph of, you know, your latency responses for your application for a particular like endpoint, you might see that there might be a peak, like the main peak on quite a low latency, and then another peak on a slightly higher latency, which is basically where the GC is kicked in and put a delay, a pause in, put an offset basically on all those response times. With the Enterprise Edition, and this is only available on Linux, it's not available on OS X, the G1GC, there's an implementation of G1GC that's available. So you basically see much better performance. You don't have these stop the world pauses. So you know, depending on which version you want, I mean, it's entirely up to you whether you want to use the open source or the enterprise version. But there's different garbage collectors available, and you know, maybe with time we're going to see more GCs available in native image. The last thing, because I think I'm right up against the time now for this session, was the last thing I really wanted to talk about was profile guided optimizations. So when you're running a Java application, what happens when you load your classes is that they're passed to an interpreter. The interpreter is slow, you know, but it runs them and it profiles them and it gathers information about, you know, what methods are hot particularly and what data is passing through these methods. And it's that kind of combination of the context in which they're run and the code that's being run, this kind of profiling information that is then passed to the JIT compiler that enables Java to make your code run really fast, right? It's able to specialize it based in light of the environment it finds itself in. You know, it might know that a particular code path is unlikely to ever run. You know, particular variables are always going to be false, and it will assume that it is false until it finds out otherwise, and it puts a guard in place to de-optimize and handle situations where it's guessed wrong. But by making these guesses, it lets it optimize the code maybe more so than it could, you know, if you were doing compiling statically, you know, before you know what the application is doing. Well, with native image, when you've built the native image, all of the code is statically compiled to native platform specific native machine code. So if you're running, you know, on Linux x86, that's the machine code that you've got. It's not interpreted, there's no intermediate level, it's running native machine code, which is great because it's fast, but you could lose some useful kind of profiling and optimization possibilities there because you're not aware of what's happening to the application when it's running. So you know, they've taken this idea and they've created a kind of out of band optimization. When you run a native image, it's possible to instrument the native image, and I'll show you. Basically, very simple to do, right? You pass the flag in. You say, I want to instrument it, PGO instrument the native image. The native image you can then run. You can run it against a representative workload, and it will capture this profiling information and save it to a profile file. We can then feed this profile into the next round of building a native image, right? So if you imagine the first pass is native image that isn't particularly optimized, but then you capture profiling information, and that profiling information then feeds into the next phase of native image generation, and that generates, you know, more efficient native images. And typically what you might see is maybe an improvement in throughput, like a maybe 20% improvement in throughput by using this PGO, profile guided optimizations. So it's a way to push the envelope on the performance of native image, because if throughput is what you really care about, you know, using Graal in a JIT mode or using a Java runtime is going to give you the best performance because of the way JIT works, right? But if you know, by using the same kind of analogy of capturing this profiling information and passing it back to when we build native images, we can start to approach, you know, very similar kind of performance as you might get with a Java runtime. And there's a lot of work going on at the moment to, you know, consistently improve that. So I kind of watch this space. It's available at the moment. It's part of the Enterprise Edition. It will improve the throughput performance of your native images, and we expect to see more and more improvement with that over time. And I somehow, without going through all of the workshops, I really have now finished. So I hope this was interesting, and at least in part to some of you, and gives you an overview of what native image is. Please take a look at the workshop yourself. It's online. You know, let me know if you find any faults or anything factually incorrect or any typos, whatever, things that don't work. Always happy to correct them. You know, just let me know. And pass it over to you. Anyone got any questions or? Everyone's dead. I've killed you all.
Well, I have one more, but I've done a lot of speaking, so I'll ask
No, not
anyway.
at all. God, it's a nice break for me.
What's the story on debugging? I mean, I presume it's not simple, but like, if my native image behaves differently, what do I do?
So, so the story is basically, you know, obviously, you know, native image is an optimization step. Yeah, obviously make sure that your Java application works and you unit test it and all of those kind of things beforehand. Then, you know, move to native image. That's the first thing to say. With the community edition, you can't debug it currently. There's no support. There's no support for that. With the Enterprise Edition, I mean, we have the ability to generate heap dumps and also to use GDB to you know, debug the actual native image. It's perhaps not the most sexy debug experience, but you are able to debug it. I mean, but you know, I get asked this question a lot, and some people I work with say, you know, why do you want to? You know, just think about it at the level of the container. You know, your application hopefully is like dumping a lot of information to log files if things go wrong and giving you or if you're using, you know, some sort of, I don't know, Prometheus and that kind of thing, Grafana, you're able to capture a lot of information about what the application is doing when it went wrong anyway. So, you know, I can sit on the fence in that, and I can sort of see both sides, really. It's a very diplomatic answer, isn't it? Sorry.
Thanks.
No, it's a good question though, right? So long and short, it's available in the Enterprise Edition. It's not the sexiest experience. CE, you can't do it. Community Edition, you can't do it. Any more takers? Please tell me I haven't like bored you to death. I do a lot of these presentations and I'm getting really sick of listening to my own voice. I'm sure there's some sort of phobia, fear of one's own voice.
Just a comment, Kris, not a question.
Hi, Manny.
Hi. I'd say very good style, better than just showing a lot of slides that we have to consume and remember. rather than that show us code and shows how it works. And
even when it goes wrong.
Yeah, I mean, what's the definition of going wrong? We do that all the time when we're working in production and even when you're writing code, right? So nothing's perfect. And if you don't make mistakes, you don't learn and others don't learn. So I mean, there's no perfect world. In this current situation, I think this is the best of both worlds, isn't it?
Well, a smart man learns from other people's mistakes, somebody said to me once, and I've always learned from my own. So,
well, hopefully your next take will be an improved one. I'm not sure if I'm going to do it here or you do it somewhere else, but.
No, but thank you for the feedback. So, I mean, for everyone else, I mean, I'm literally just trying this out. It's just an idea to, basically based on an idea of another colleague of mine, Oleg, to maybe make things a bit more interactive. But I mean, if it works, I'd like to know. If you think it's awful, I'd also like to know as well.
I find it useful. Yeah, it was good. I learned some stuff. So I knew some stuff I'd looked into before, but yeah, it's give me good context. So that's very good.
You've grown quite the beard, Steve, since I last knew you.
Coronavirus, yeah.
And it's really great that you folks are keeping that high tension late in the evening. In Germany, it's 1 hour later, and that's really a proof for the community outside that people really like to keep that going on. And it will be on your YouTube channel. Of course, it's recorded. And it's awesome for 8 steps, these workshop to follow on and keep tension and asking questions, and that's amazing. So thank you, folks from London Java community.
Yeah, very much agree with Wolfgang. Thanks for listening in, and please do criticize in a constructive way the GitHub repo. Correct anything if you see any typos, errors, whatever. Always happy to be informed of them. Cool. I've had quite a long day, so I'm finished with talking now. So unless anyone else has got anything else, you know, I'm quite happy to finish. Unless you've got any other questions, anybody wants to ask anything about GraalVM or would like to.
Yeah. Sorry, I have one last question. What about license? The license. I mean, the community edition, is it free? Can I build and distribute my application?
The community edition is free. In terms of distributing like native images, there's, I think, is it GPL?
Yes, it's GPL version 2.
GPL license version 2. So, you know, be aware that like if you are distributing your native image, I think GPL 2 would, you know, if you're packaging in some other GPL product, it could be that you were required to, you know, make your source code available. But like in, you know, in the personal realm, or if you're operating with inside, I'm not a GPL lawyer, right? But as I understand it, if you're operating inside a boundary, you know, of an organization, then you can use the community edition. You can use it in production. Absolutely nothing stopping you doing that. Lots of people are. The enterprise edition is OTN licensed, Oracle Technology Network licensed, and that means that it's free for evaluation, personal use, development. They only care about, and it's licensed on a subscription model, and that's only in production. So, you know, if you're using enterprise edition in production, then you need to license it on a per CPU basis. But yeah, go ahead, use community edition to build apps, if that's what you want to do. We hope that you will think that the enterprise edition has like sufficient features and support that makes it worthwhile. I mean, that's one of the main things. It's supported by the people who wrote it, and that level of support and security, basically, in terms of like quarterly patch updates, you know, fixing issues, being able to have that dialogue with the people who built it is meaningful and worthwhile, as well as the, you know, non-functional differences such as performance. Sales pitch over.
Kris, what's the scope with creating native images out of non-jar files and non-JVM languages. Well, I don't think that's the right question, but languages that run on the GraalVM because of the polyglot mode, but they don't produce bytecode that we can create class files and jar files from to create native image from. Should they not be possible to be converted into native images since they are already running on the GraalVM?
So it depends, I think. I mean, this is, I have to admit, not an area of expertise for me. So if you build, so for instance, if you are on Node.js runtime, right? The Node.js runtime is native. You know, where possible, we use native, like our JIT compiler.
Right.
We've made a native version of our JIT compiler because there are reasons for that. It's got performance benefits. When you run your JavaScript, it basically is baking in the interpreter. If you, say, for instance, you're using a truffle. So how truffle works, you write an interpreter for your AST, for your language, say like JavaScript or Python or whatever. And that interfaces with this truffle layer and like this common object layer underneath. Like I say, it's not a super area of expertise for me. But when you would say, when you build a native image, you're going to basically build a native image of the interpreter, not necessarily of the code that's being run. Now with JavaScript, I don't think you can really, as it stands, I'm not entirely sure about this, but I don't think you can build like a native image of your JavaScript. You can package it up, but I think the interpreter still runs. But I don't, take all of that with a pinch of salt because it's not something I look up very often, so I'm not entirely sure. An interesting thing though is that now we have a Java JVM implementation built on top of Truffle, which means you can build a native image of Java that still can dynamically load Java classes. So you can build, my head hurts when I say that as well. You can build a Java app that's a native image and has got like all of the native image, performance characteristics, fast start time, low memory. But you could still kind of have your cake and eat it. You can do things dynamically. You can load classes dynamically because the JVM, the interpreter for the JVM basically is natively compiled, but it's still there. The JVM is baked in. This interpreter for the JVM is baked in. So it's able to dynamically load in things from the environment, say a class file, and interpret it, as well as your other Java code that you wrote for your application. If you can imagine this, that's natively compiled to native executable code, but you're also baking in a JVM. So and the two things can talk to each other. So you can have your app being like native, fast starting, all in, native code, but there's also a JVM available because of the implementation now of Java on top of the Truffle API. And even madder things, you can load a Java runtime inside a Java runtime inside a Java runtime. So it's like, I think it's it's fully meta-circular, right? So there's some interesting new and quite exciting capabilities coming with the 21 release. This is one of the main things we finally released as experimental, the Espresso language, which is our Truffle implementation of Java. So, there's quite a lot of interesting stuff there.
But how big is the native image? If you're packing in the JVM into that native image, we are back to square one, aren't we? Because in the JVM mode, we do have, well, the JVM mode. Okay, it'll be the JDK plus a stripped down version of your app, but it still be good parts of the JDK, right? If you have the JVM built into your
I'm not actually sure on that. I can't answer that one for sure, but I think there are still, certainly performance optimizations, right, in terms of startup time. As to how much has been packed in, is it smart enough to know that not everything needs to be there? I don't know, because the substrate VM, remember that we package this stripped down VM as our interface between our code and the world. Sure. So for thread execution, like talking to the file system, network, whatever, it's all through this substrate VM layer. So, maybe some things won't work, right? We're probably deliberately throwing away, chunks like security loader isn't available in the native image because we don't need it. But is that in the Espresso? I don't know. I mean, it's only just released in 21, and I have unfortunately been too busy to really take a look at it. But I know that there are some very interesting things that you can do with it.
Well, it'll be interesting to see if the truffle-based languages, even though they're interpreted, they can produce some sort of a, because they are actually, they do have a map to the machine code per instruction that they're reading, right? Because that's what it's doing, from what I understand, that internally the language, the native language is mapped to a bytecode, which is mapped to the machine code. So would it not be possible to then dump that into some sort of a binary image, which then can run? I don't know. I'm just saying.
I'm not entirely sure.
From a theoretical point of view, because if you can run it on the JVM, then you already have, just like we are able to do with the native image, because we could run it, you already have a map of the heap of the image of the binary that's running in memory, which is what we're dumping into the binary file, which then becomes your native image.
Yeah, I'm not sure. I mean, when I first joined, I asked a similar question of the guy responsible for JavaScript, and I think there's, it's certainly in JS there are certain very dynamic aspects of it that we may not be able to get around. The one maybe I should look at is Ruby. That's probably a good example of whether this works or not. I generally don't do a lot of polyglot stuff. I think in many ways this is like one of the most important features of GraalVM, the multilingual functionality, right? That not everyone when you're implementing a language, you maybe you could implement. Why write your own JIT, right? Why write your own language runtime? Why not use something like Common Language Runtime from Microsoft, or Java, which is what people use. They were building things that basically transpiled things into bytecode, and then you would run bytecode. But they're not always necessarily a good fit for various reasons, as I understand it. But with Truffle, the fact that you can implement your language at this kind of AST level gives you a huge amount of flexibility, and you get all of the performance benefits and the stability benefits of the JVM as a runtime, right? And you can take advantage of the Graal JIT, which is really performant. So there are lots of things, and there's also the one thing I didn't touch on, and because probably I don't really understand it properly, that we have the ability to specialize the interpreter for a language with your program, so that what actually is run, what gets passed down to the JIT level basically is a specialization of your interpreter given the program that you've asked it to run. And that obviously leads to some very interesting performance optimizations that you couldn't have just in the interpreter alone. And maybe that's going to help us become really, really performant. Things like that offer opportunities to become really super performant, especially in the JavaScript world.
Kris,
definitely
maybe,
done with talking now.
Kris, maybe this is something for a new session, Java on Truffle. Truffle.
I was just thinking that.
Because it was one of the new features from last week from version 21, a new component, and running Java on Truffle as a JVM, and that could be really a dedicated session if someone is interested in that. With the stuff we mentioned earlier, the espresso, but it's confusing if you jump directly into that, without the other things around from Graal. So it's definitely worthwhile to go into Java on Truffle within this new feature, but it's brand new since last week.
Yeah. I'll plus one that, because that's a whole new world. The polyglot and the Truffle world is a whole new world that most of our Java developers are not familiar with, both from the implementation and
I'm trying to get my head around that as well. It's confusing at first when you're thinking about it.
We'll start writing something, and maybe we'll do a session here in 3-4 months, maybe. Give me a break. But yeah, I think that like, yeah, a good demo and a good description of espresso, when like one that's meaningful, that where we properly understand what's going on rather than just being too hand wavy. Cool, thanks everyone. I don't know how this ends, if I just have to close it down or if...
Thanks, Kris.
No worries. Steve, stay on the line. Your call is important to us. Thanks everyone. Hope it was useful.
Thank you.